to chapter 13. So you should have saw that your exam 2 got graded. I will be posting the solutions up either today or tomorrow. Okay, so you can take a look at the solutions compared to what you had there to see what you did or didn't do, and compare it. I'd see the most issues were with the diagrams consistently across the tests would be with the vapor compression one, where things were a little modified, and the Brayton cycle, where things were a little modified differently than the ideal case. So those two were, I'd say, more consistent of what people got wrong across things. The other stuff was more dependent upon the person, if they had something wrong in the other parts of the problems. Depend upon each person of what they saw and what they did incorrectly. Okay. All right, so we're on to chapter 13, unless there's any questions. The 13 is just today. We'll do all of chapter 13 today. It's more like a little bit of basically a chemistry chapter of looking at mass fractions, mole fractions, molecular weight, and how do we apply that to mixtures. Okay. All right, so if we, our objectives, we're going to be looking at those compositions, like I said, mass fraction, mole fraction, we'll do a little bit of volume fraction, okay, and then we'll be dealing with ideal gas. We don't really do the real gas part in the chapter, okay. So we make the ideal gas assumption, okay. So if we think about the composition of a gas mixture, so with mass and mole fractions. So if we think, here's with mass, conservation of mass holds, right? If we have a mixture of hydrogen and oxygen and it's 38 kilograms, it can be made up of 6 kilograms of hydrogen and 32 kilograms of oxygen, which you sum that over, you have 38. Right? If you think about then the mass fraction of what's in here, for the hydrogen would be 6 over 38, and the oxygen would be 32 over 38, right? You can calculate that out, and that would be the mass fraction for each of those components in that total mixture. Okay. If we think of moles for a non-reacting mixture, okay, so this mixture is not reacting, okay, so that means the moles are not changing. If it was reacting, like we'll see in chapter 15, now the moles can change. Mass can't, but moles can change, right? You can get different moles and move around if things are reacting, okay, so, but if it's non-reacting, we can just look at the total. So here we have 4 kilomoles, and if we want to look at the hydrogen mole fraction, that would be 3 over 4, right, or 0.75. Oxygen would be 1 over 4, or 0.25, okay, of its mole fraction. Okay, so we have the molar analysis or the mass or gravimetric analysis. So if we wanted, so this little subscript M is the mixture. Okay, so if we wanted the mixture's mass, we just sum up all the components. Okay. If we wanted the moles of the mixture, okay, we just sum up all the components. That's what that is, sum up all the individual. So that's what we did right here. And that's what we did for the mass right here. Okay, for mass fraction, we took that mass of the mixture and then the mass of the individual components, 6 divided by 38. And that's the mass fraction right here of hydrogen. And then we did the oxygen one. Okay, which was 32 divided by 38. And then we have the mole fraction, right? Just the mole of the individual component. So the I just means individual component. Okay, and then again, M is the mixture. So the total is 4, and we took the individual 3/4 and then 1/4. That was our mole fractions for those. This slide more just shows you how to go from one thing to the other. And the big thing that does this is our molar mass, right? So our molar mass of an individual component is the mass of that individual, right? It's mass over moles, right? So if you think of the molecular weight or the molar mass is the individual mass is, and then the mole of that individual, right? If you think about it in units of SI, that would be kilograms per kilomole, or English units, it would be pound mole over, or sorry, pound mass over pound mole. Pound mass over pound mole, okay? And we can use that to go from mass to moles, or from moles to mass. All right, so let's first start we'll use the mixture's mass, or the mixture's molar mass. Okay, so this is the mixture's molar mass, which is the mass over the moles, right? Well, we can start bringing in the equations we had in the last slide. So for mass, it's just the summation of the individual components, right? Now we can use that mass of the individual component and put in our equation right here. And they're basically just rearranging. So then the mass of the individual component is the molar mass of that individual component times its molecular, or molar mass of the individual component times its moles, right? So they're just now plugging that inside. And if you look at this one now, when it's rearranged, this Ni over Nm is just the mole fraction. Okay, so we just using the substitution of different equations, we rearranged it to get this version. Okay. Gas constant of the mixture, which is useful if you want to use the ideal gas law. Right, we have PV equals, let's do the specific volume version for now, RT, right? Well, this is the gas constant. If we're applying it to a mixture, we need R of that mixture, right? We would need pressure, volume, we'd need the gas constant of that mixture, right? So here's the way to get the gas constant of the mixture. You take the universal gas constant and divide it by the mixture's molar mass. So we'd have to get the molar mass of that mixture. All right, so another version. So again, we're starting with the same equation right here, but we're going to substitute on the mole side instead of the mass side. Okay, so here, now we're going to leave the mass side alone, but instead for the moles, we're going to use the molecular weight equation, and that just has so we're just rearranging this equation for the moles, right? So we have Ni equals the mass of that individual component divided by its molar mass, right? So if we do that here, we substituted in the summation of all the individual ones is just the mass over the molar mass of the individual. And now here, basically they just took this mass of the mixture and divided it. So divided on the numerator, which brings it down on the denominator. And we see this mass I over mass M is just mass fraction. So they created an equation here to go from mass fractions to get your molar mass. So mass fractions, and you would need the moles of the individual, or molar mass of the individual component. And here, up here, we had to get the molar mass, we just needed the mole fraction in the molar mass of the individual component. If you want to go straight from the mass or mole fraction to the mass fraction, we have mass fraction is just the individual component, right, divided by the mixture's mass. If we put in our equation here, but for mass, okay, so we put this in here, substitute it in for the mass, do it for the mixture. Well, this over this is the mole fraction. So then you just have the mole fraction, molar mass, the individual component, the mixture's molar mass, and we can go from mole fraction to mass fraction. Oh, last equation is, if you sum up all the fractions, whether it's mass fraction or mole fraction, they should equal 1. Okay. All right, so we have two different kind of laws of how to look at things of these ideal gases for the PVT behavior. Is we have Dalton's law, which is additive pressures, and we have Amagat's law, which is additive volumes. Okay, what does that mean? So for Dalton's law, if we take gas A is at the volume, the full volume, and the full volume and the mixture's temperature, gas B is at the full volume and the mixture's temperature, and solve for the pressure of gas A and then solve for the pressure of gas B using ideal gas law, we add those two pressures up and we would get the total pressure. Okay. An example of this is if we look in basically our room that we're in, we have air, there's dry air in it, and then there's water vapor because you have humid air. So if we think of that water vapor as an ideal gas that's in the air, then there's the pressure from the dry air and then the pressure from the water vapor, and you add those up and you get the pressure of your room that you're in. Okay, so you have the partial pressure of the air, partial pressure of the water vapor, and that gets you that total pressure of the room. So if your room is 100 kPa, it's the partial pressures added up to 100 kPa of the individual components. All right, so then the other method is now instead we're taking gas A is at the total mixture's pressure and temperature, and gas B is at the total mixture pressure and temperature. And we use the ideal gas law to get volume, use the ideal gas law for B to get volume, you add them up and you get the total volume. Okay, so you either have to hold volume and temperature as the mixtures, or you hold pressure and temperature as the mixture. One does the additive pressure, the other does the additive volume. Okay. All right, so if we take those two together, right, if you add the individual pressures, you sum up all the pressures of the components, you get the total mixture's pressure. You sum up all the volumes, you get the total volume pressure, right? And they're showing you what you keep. Temperature and volume of the mixture. Here you get temperature and pressure of the mixture. The next of this is we have the components pressure, right? It's right here, right? Components volumes right here. There's a pressure fraction, which is kind of basically in the volume fraction, right? This PI divided by the pressure of the mixture is the pressure fraction, and VI divided by the mixture's volume is the volume fraction. Okay. For ideal gases, whether you take one law or the other, you're going to get identical laws or identical results. You just got to hold true to one or the other. You can't mix the two together while you're calculating something. So you calculate everything out with Dalton's law, or you calculate everything else with Amagat's law, you're going to get the same results. Okay. So here's the example of oxygen and nitrogen. So this mixture has that pressure, temperature, and volume. If we used Amagat's law, 100 kPa, temperature is the same, so we're using the mixture, and then you calculate, you get for the oxygen takes up 0.3 meters cubed, nitrogen takes 0.7 meters cubed. You sum them together, you get the mixture's volume. Right? That's Amagat's law. All right, so what does this mean for those pressure fractions and volume fractions? Well, let's show it for an ideal gas. If we put that PI and the PM, right? If we put in the ideal gas law, right? So from mole version, right? So it's the mole version with the universal gas constant. If we want pressure, we have to move volume over, so that's what you see here, right? So this is for the individual component, okay? So it has a universal gas constant, the mixture's temperature, volume, and then the mole fraction, or moles, sorry, for that component. The mixture puts everything at the mixtures. Okay, so when you look at this, gas constant cancels, mixture temperatures, volume cancel, and you're just left with moles of that individual component divided by mixture moles, which is the mole fraction, which is the definition of the mole fraction. Here, we have volume of that component. Okay, so we're just taking ideal gas law and instead solve for volume, okay, and plug that in. So we put that in here for the individual component, right? So RU, TM, PM, because temperature and pressure at the mixture. We have mole for the number of moles, and then here it's for the mixture, so everything's at the mixture. Well, these things cancel out again. You're left with moles of the component divided by the mixture. So you have the mole fraction. So the partial pressure of that component divided by the mixture's pressure is equal to the mole fraction. Right? So this shows you how you can rearrange it. So if we rearrange that, we can get the partial pressure of some component by its mole fraction in the mixture pressure. Okay, that'll become useful in the next chapter and the chapter after. If we think about, let's say, chapter 15, let's think about if we calculated the mole fraction of water vapor leaving your tailpipe of your exhaust of your car, right? And we know that pressure of the mixtures, it's being released into the atmosphere, 100 kPa. Then we would know the partial pressure of that water vapor that's being released into the atmosphere. And that actually, when you get to the next chapters, would tell us about the dew point, and we'll talk about what that is later on. But that information is useful, okay, the partial pressure. Okay. It's non-ideal, which we won't really get into, we're assuming ideal, but the volume fraction and the mole and the pressure fraction might not be identical because we use ideal gas law to get them identical, right? When you're measuring gas fractions, say exhaust gases leaving a combustion chamber, or you're taking sample of an exhaust stack, maybe from a natural gas boiler or something like that, a lot of measurements measure the fraction directly. The mole fraction is what they give you, and then you use that to convert to whatever you need. The instrument would give you the mole fraction of that component. So you have an instrument that measures CO2, it would give you that CO2 measurement. All right, so then we have mass fractions, mole fractions, pressure fractions, volume fractions. We use all this. Now, how do we use those to get properties? Okay, well, if we're looking for internal energy, of the mixture, right, we just sum up the internal energies of each component. Or if we need that this is capital, and we just take lowercase times lowercase, so lowercase mass, lowercase, basically the per unit mass, internal energy multiplied times mass. We can also use mole version instead, right? This is mass, So if we had kilograms, this would be kilograms, kilojoules per kilogram, right? And the kilograms would cancel, so you get kilojoules, which is units of the total internal energy. If we did it per moles, that's what this bar is. Okay, the bar over the internal energy is telling you it's per kilomole or per pound mole. So if we did that one, let's say that's kilomoles times kilojoules per kilomole, then the kilomoles cancel and we're still left with kilojoules. Okay, so it really depends on what's the better way to do it. When we deal with reacting systems, a lot of times we deal with moles because we have chemical balances of moles. So in chapter 15, we're balancing a reaction. So we'll have the moles is more readily available than the mass. So we use this kind of version. Okay, and when we were dealing in the earlier chapters, we used more of the mass because those are readily available, right? All right, so we can do this same process for enthalpy and entropy. Okay, changes, this is just changes down here. It just makes the delta in there, right? So we just put the deltas in there, okay, for the change. All right, so if we now wanted the mixtures per unit mass, okay, so this is lowercase u of the mixture, we take the mass fraction times that u. Okay, so the easiest way to remember this and then is if the property you're looking for is per kilogram, so per mass, you're going to use mass fraction. Okay, if the property's per kilomole, you're going to use mole fraction. Okay, so the individual components mass fraction times its per unit mass internal energy. Here's the individual components mole fraction times its kilojoules per kilomole, and then you sum it all up for each component to get the mixture. And do the same thing for enthalpy, entropy, CV, and CP. All right. If you're looking for the per unit mass, you're using mass fraction. If you're looking for the per unit moles, you use the mole fraction. Okay. All right, so one thing is if you need to use the change in entropy of an individual component, okay, we have, we know from ideal gas, delta S is, we've had this for variable specific heats. Right, we had, let's say this one, that's what they show here in a second, for constant specific heats. All right, so this is, we can use this version, let's say this one directly if we have the mixture. If we want the change in entropy of the mixture, we just use that, okay? We would just need the mixtures T2, T1, P2, P1, the mixture's gas constant, the mixture's CP. Okay? Now, if we wanted change in entropy of an individual component, okay, so that's not of the mixture, but just one component in the mixture, we have a variable specific heat version right here, constant specific heat version right here. So this is, that variable specific heat change of this CP natural log T2 over T1 for that component. Okay. Here, the biggest thing is you have still the gas constant of that component, not of the mixture, right? But the pressure is of the partial pressure of that component in the mixture. So it's not the mixture's pressure that's right here. It's that pressure of that component in the mixture. So you would get that with taking the mixture's pressure times the mole fraction of that component in the mixture. Okay, so this would be here. Oh, that's state one. Sorry. This one would be here, right? and then this one would be here. So this is the concept-specific heat version with CP for that individual component. T2 over T1 is typically of the component is the mixture's temperature for 2 and 1. All right, so that's it on the slides. Any questions? We'll do an example.